Hello friends, welcome to my channel. Let's have a look at problem 95, Unique Binary Search Trees 2. Hello friends, welcome to my channel. Let's have a look at problem 95, Unique Binary Search Trees 2. In this video, we're going to share a treatment or solution based on recursion. So first, I'll read through the statement to digest the problem requirement, and then we do a simple analysis, and finally we share the code and explain the code. First, the statement. Given an integer n, return all the structurally unique binary search trees, which has exactly n nodes of unique values from 1 to n. So return the answer in any order. So here are two examples. In example 1, so the number of nodes is 1, so there is only one binary search tree. So this corresponds to this output here. It's a list of lists. So in example 1, so there are different structurally distinct trees. So we have 5 of them. So that's the output here. So notice that the constraint for this problem is that n is bounded above by 8. In other words, this n is very small. So with that said, so actually we can have a feeling about the problem size. So here, let's give a treatment based on recursion. So here we feel that recursion is a very natural solution to this problem due to the binary search tree structure, right? In particular, for binary tree, it's a recursive abstract data type. And then in this problem, we are going to take into consideration of the binary search property. So the binary search property says that so the left subtree node's values is less than the root values, and the right subtree values is strictly larger than the root values. And this relation is recursively holds for any subtrees. So actually, we can build all the binary search trees using by choosing different values as root, and recursively do this for the subtrees. So here the key observation is the following. So if we use I as the whole tree's root value, then we need to use values smaller than I to build left subtrees, and correspondingly we need to use larger values to build the right subtree. So here the values used to build the binary search trees are given by 1, 2, 3 up to n, right? Both n 1 and n inclusive. So with that said, actually, so writing the solution for this problem is sort of routine. So here we are going to do the following. We are going to write a hyper function to do the binary search tree generalization, and then we call the function. So first, let's make a preparation. So we define a hyper function. For this, I'm going to just call this function helper. So the hyper function, because here we know the min value and the max value for the values we are going to use, let's put them here. So the left and the right are the integers, or the upper bounds and lower bounds for the values. And then we're going to use this left and right to build binary search trees. So first, if left is larger than right, so in this case, so we are going to return null. Right. So you can put a comma here to indicate or emphasize that this is a list. So or I can just put it here. So this is the one case. Another case is if left equals right. So this case corresponds to a single node binary search tree. So this is actually an easy case. We just need to return tree node with node value to be either left or right because they are the same, right? So this is another case. Then for the generic case, so we're going to initialize a result variable, and then we can choose any value in between left and right and as a root value, and consider building the corresponding left and right subtrees. So here left and right are both inclusive. So what we are going to do is for I in range So left, so this includes left. So here we write right plus 1 to include the right point. And then what we are going to do is to first we can get the root value, right? We can get the left side. So left subtrees. So let's call it left side maybe. So it's hyper left, so up to I minus 1, right? And the right side, let's see, I'm going to use hyper. So we are going to use these values from I plus 1 up to right. So we right. So this way we get the left subtree list and the right subtree list, and then we can actually build the result for this whole tree. So now for L in left side, so L is a binary search tree. For R in right side, so what we're going to do is we initialize or instantiate a root tree node. The root value will be the I, right? And then we are going to connect the root with the left subtree and the right subtree. So root left. So we can do this actually. So we can do left equals left, right equals right. So then what we are going to do is to append this tree to the result, and then finally we do the return. We return the result. So here I want to point out that the return of this hyperfunction is a list of valid binary search trees, right? So here, like we built the result, so here is a tree, right? Once we finish building a tree, so we append the tree to the result list, and then finally we return the list. So this is actually the hyperfunction. So now let's look at the problem logic. So with function call and return. So we're going to return hyper. So the left value, that is 1. So the right value is n for our problem. That's it for this current problem. So I guess now we are ready to do a check. Yeah, it passes the case for value 3. So actually we can check for 1, 2, 3, 4, 5, 6, 8, right? So let's do 8. Yeah. So actually a natural extension for this problem is count how many unique binary search trees are there for given an n. So this actually corresponding to another problem, that is unique binary search trees. This is counting the number of distinct binary search trees. So let's also do a generic check before we end this video. Yeah, it passes all the cases. So with that said, I guess that's about it for this video. Thank you.